So in this part, we are going to study Fermi energy level and mass action law. Fermi energy level is a theoretical concept and says that the Fermi level lies in between the conduction band and the valence band for an intrinsic semiconductor. Mass action law says that the product of number of electrons and the number of holes is constant. So we are going to study this too in this lecture. So let's proceed. Okay, so now let's start the next topic, Fermi energy and mass action law. First of all, let us discuss about Fermi energy. What is Fermi energy? So basically, the Fermi energy is a quantum mechanical concept and is usually refers to an energy of the highest occupied quantum state in the system of fermions and at absolute zero temperature. This definition looks quite difficult. Let's see a simplest version of this, right? So the Fermi energy level. So basically it's a level, right? So this Fermi energy level is a maximum energy. See, Fermi level is a maximum energy which can be occupied by an electron at absolute zero. That means at 0 Kelvin. So if we have an electrons in our material, right? So maximum energy which an moving electron can occupy at an absolute zero temperature, that will be called as a Fermi level, right? And this represents basically in probability of an occurrence of any electron at this absolute zero temperature in any material. So if we see, let us see where this level will lie in our energy band diagram. That is most important for us to understand, that where this level will lie in the energy band diagram. So we have already seen that energy band diagram has three basically bands. One is called as the conduction band, other is the valence band, and this is the forbidden energy gap. Okay, so we see here, so basically we are seeing for a case of intrinsic semiconductor. So for an intrinsic semiconductor, the Fermi level lies at the middle of the forbidden energy gap. Let's suppose if this forbidden energy band gap is of 1 electron volt, so it will be of at around 0.5 electron volt. That means at the middle of the forbidden energy gap. So exactly at the mid of the forbidden energy gap, the Fermi energy level lies for the case of intrinsic semiconductor. It is not, I am not talking about the extrinsic. If we are having an extrinsic case, then this changes, and that what and how it changes, that we will see in the next slide. Now let's see the Fermi energy diagram for an N-type semiconductor. Now we already know that what are N-type semiconductor. So the semiconductors which are doped with the pentavalent type of impurity. Okay, so that are called as the N-type, and we know that in N-type semiconductors, their majority of the charge carriers are through the electrons. So the current basically is through the majority charge carriers electron. Okay, so if we see in this diagram, so again the conduction band and valence band. So let's suppose this is a donor energy level. Since we have added the impurity donor atoms and donor impurity atoms, so that will have an energy level, and that is lying somewhere near to the lowest energy level of the conduction band, that is somewhere here. So the Fermi energy level, now we have seen that in case of intrinsic semiconductor it was at the middle, but we see that whenever we changes from intrinsic to N-type, the semiconductor, the Fermi energy level has shifted upwards, that is towards the conduction band. So we can say that the Fermi energy level shifted upwards towards the bottom of the conduction band. So it has shifted, okay, upwards near to the bottom of the conduction band for the case of N-type semiconductor. Now let's see where it shifts, let us see where is the position of Fermi energy level for the case of P-type semiconductor. right? And we already know that p-type semiconductors are basically the semiconductors which are made by adding the trivalent impurity atoms, okay, also called as the acceptor impurity atoms. So if we add the trivalent impurity atom, so the Fermi energy level shifted downwards towards the top of the valence band. So it shifts downward. This is most important to learn for us, right? So whenever we changes the semiconductor from the intrinsic to p-type, so the Fermi energy level which was earlier at the mid of the forbidden energy band gap, now it has shifts downwards, okay, downwards near to the highest energy level in the valence band, okay. Now let's see mass action law. What is this mass action law for any semiconductor? So addition of n-type impurity decreases the number of holes below a level. When we are adding up the impurities and making a semiconductor n-type, that will decrease the number of holes. See, the decrease in the number of holes does not mean that the number of holes are decreased. This means that the number of holes relative to the number of electrons, since we are adding n type of impurity, donor type of impurity, so we will be having more number of electrons with us as compared to holes. So we can say that effectively from as compared to intrinsic. See, in case of intrinsic semiconductor, we were having number of electrons is equal to number of holes, but as we convert an intrinsic to an n type, the number of electrons has increased. So we can say that all the number of holes has gone below the level compared to the electrons. Similarly, on addition of p types impurities, okay, decreases the number of electrons below a level. In case of p type semiconductors, the number of electrons decreases because we know that the majority charge carriers are holes, okay. So it has been experimentally found that under thermal equilibrium, so at the equilibrium case for any semiconductor, whether it is an intrinsic or extrinsic, okay, it does not matter. So for under thermal equilibrium for any semiconductor, right, the product of number of holes and the number of electrons is constant and independent of doping or amount of doping. Right. So what this mass action law says that the product of number of holes and the number of electrons, this is constant. So if you multiply, if you do the product of number of electrons and holes, this will basically a constant, use a constant value, and that will not depend upon the amount of doping. Whatever amount of doping we do, that does not depends upon. This product is constant. Okay. So now let's see the relation. This relation is known as the mass action law, and it is equal to n into p equal to ni square. So here n is basically an electron concentration and p is a hole concentration and ni is a intrinsic concentration. So this law says that the product of electron concentration and the hole concentration is equal to the intrinsic concentration. See, we have seen in case of intrinsic semiconductor that in intrinsic semiconductor the number of electrons is equal to the concentration of electrons is equal to the concentration of holes is equal to the intrinsic semiconductor, right, and the product of this n into p will be equal to ni square, and this is what this mass action law says, and this will be constant. See, right now we have this seen for the intrinsic case. Now maybe if we see for an extrinsic, let's suppose n type or p type, for both the case this relation will hold, okay, this will not it is independent of the semiconductor type, okay. So let's see the charge carrier concentration in n type and p type semiconductors, okay. So now let's analyze what are the charge carrier concentration in n type and p type semiconductors. See, free electrons and hole concentration, okay, they are always related, okay, by law of electrical neutrality. So free electrons and hole concentration, right? So there will be always a relation between these two, and that relation, the relation is called as the law of electrical neutrality, and it says that total positive charge density is equal to the total negative charge density. This means that, let's suppose we take any semiconductor, whether it is an N-type, P-type or an intrinsic semiconductor. So you just take out, bring any semiconductor, so piece of any semiconductor slab, and you just put it down there on the desk, and if you will observe it, so there will be a total positive charge density in that material will be equal to the total negative charge density, or we can say it is the charge is neutral. So the number of positive charges are equal to the number of negative charges. So this is electrically neutral will be there, right? So this is what this law says. Okay, so law of electrically neutral. So for any semiconductor, whether it is a P-type, N-type or intrinsic, the total positive charge density will be equal to the total negative charge density. Now let's assume that ND, capital ND, is a concentration of donor atoms. Okay, and it is equal to number of positive charges. See, donor atoms are always represented, or they are termed as they are assumed the charge to be the positive charges, right? Because they are ready to donate, right? So they are having excess number of electrons with them, and they are ready to be paired with any positive, any free, they are ready to be paired with the neighboring silicon atoms, right? So therefore we assume the charge of donor atom as a positive charges. Okay, so let's assume that ND is a concentration of donor atoms, okay, or it is equal to the number of positive charges contributed by the donor ions. And let's suppose small p is a hole concentration. So small p is a concentration of holes in any semiconductor. Also assume Na. Na is a concentration of acceptor atom, or we can assume, since we have assumed, the concentration of donor atoms is equal to the number of positive charges, and same here, the concentration of acceptor atoms will be equal to the number of negative charges contributed by the acceptor atoms. Okay, so the charge of this will be negative, the charge of this will be positive, and we know that the charge of hole concentration, so holes are positive charge, and the N is an electron concentration and its charge is negative, right? And just now we have seen that the law of electrical neutrality, and what does it says that the total positive charge density is equal to the total negative charge density. So if we follow that law of electrical neutrality, so the positive charge densities, that is due to ND and P. So ND plus P will be equal to Na plus P. Okay, this will be equal to Na plus P, and this will be true for in general, right? So we can see this is either we can relate this with the intrinsic also. In intrinsic case, this ND and Na will be 0. And for that case, N will be equal to P, and we know that the number of electron concentration is equal to the number of hole concentration for the case of intrinsic one. But if we assume either N type or P type, okay, so it has the donor atom as well as acceptor atom. So we may have a semiconductor which has both type of impurities, trivalent as well as pentavalent. So we cannot directly say that what it is N type or P type. So that depends upon which is more in number. If donor atoms are more in number, it will be termed as an N type, and when the acceptor atoms or the acceptor impurities are more in number, we say that it is a P type semiconductor. So therefore this relation holds in general for any type of semiconductor. Now let's consider what if we are having specifically the N type semiconductor. Okay, so we know that for N type semiconductor, the number of acceptor impurities are 0. We are only having the donor impurities in that. So the concentration of acceptor atoms will be 0. Okay. And we know that for n types semiconductor, the number of electrons are more as compared to the holes, because the majority charge carriers in n type are electrons. So n is much greater in concentration as compared to the holes. So we can see here, so Nd, so we can neglect this P, okay, neglect this P and put Na equal to 0. So what we will have? We will have that number of electron is almost equal to the donor concentration, right? So the number of electrons will be almost equal to the concentration of donor impurity atoms in for the case of n-type semiconductor. Okay, so the concentration of donor atoms is equal to the concentration of free electrons. So according to mass action law, we know that n into p is equal to ni square. Okay, we know that the number of electron concentration is equal to Nd. Now to find the whole concentration, so that will be equal to P will be equal to Ni square by N, and N is equal to Nd. So the whole concentration will be equal to Ni square by Nd. Okay. Now let's see for the p-type semiconductor. Okay, so we know that for p-type semiconductor, basically it has only the acceptor type of impurities. So the concentration of donor atoms will be 0, that is Nd will be 0 for the case of p-type semiconductor. And we also know that in the case of p-type semiconductor, the majority charge carriers are holes. So the number of hole concentration is significantly higher than the concentration of electrons, that is P is much greater than the N. So if we assume that relation, so in that we have kept Nd is equal to 0 and we have neglected the N. Okay, so from that relation we got that Na is equal to P, that is the number of holes or the hole concentration is almost, you can say, equal to the concentration of donor atoms. Okay, that is in p-type the concentration of acceptor atoms is equal to the concentration of holes. So again, according to the mass action law, see, we know that the concentration of hole is equal to the concentration of donor atom, but we don't know what will be the concentration of electrons in p-type. So for that we are using the mass action law, and mass action law says that N into P will be equal to Ni square, and to find the electron concentration, N will be equal to Ni square by P, and we know the P, that is the whole concentration, is equal to Ni square by Na. So so from here we see that this mass action law can be applied for any type of semiconductor, whether it is an intrinsic n-type or p-type. So it is valid for any type of semiconductor. Also the concept of the law of electrical neutrality, that is also valid for intrinsic or as well as the extrinsic, okay, n-type or p-type. So it can be any type of semiconductor that will be valid for both the type of semiconductor. So again, as we are done for the previous topics, so Sam, we will be doing some question here. Okay, we will be taking 2 examples and let's see how much we have gained till now. So the question is, the width of forbidden gap in silicon crystal is 1.1 electron volt. So we are given that the forbidden gap in a silicon is equal to 1.1 electron volt. When a crystal is converted into p-type semiconductor, the distance of Fermi level from conduction band is, see, the problem basically given is we are having an intrinsic one, right, and we are already given the width of the forbidden band gap, and it is equal to 1.1 electron volt. Now we are given that, let's suppose we have added some p-type of acceptor type of impurity in it, and we have converted it into a p-type semiconductor. So now the semiconductor which we are having is a p-type semiconductor. The distance of Fermi energy level from conduction band So the distance of Fermi energy level from the conduction band will be equal to, will it be greater than 0.55 electron volt, equal to 0.55 electron volt, less than 0.55 electron volt, and equal to 1.1 electron volt. So see, we have already seen that if we draw an energy band diagram, and let's suppose this is a conduction band, and let's suppose this is a valence band. Okay, we know that initially for the case of intrinsic semiconductor, the Fermi energy level lies at the middle. Okay, so Fermi energy level will lie somewhere here, and we have seen that when we have the p-type semiconductor, in that case the Fermi energy level shifts downwards. Okay, this level shifts downwards and it comes close to the highest energy level of the valence band. So the distance of the Fermi energy level, so let's suppose the Fermi energy level has shifted now at this place. So the distance of Fermi energy level from the conduction band, that means this, will be equal to, and we are given that the forbidden energy band gap is equal to 1.1 electron volt. See, this distance is 1.1 electron volt and we want to find it out this distance. So definitely if we see this for when this at the center, this distance is around 0.55, okay, and it is greater than 0.55. So but it is not equal to 1.1. So because Fermi energy level is not touching the valence band, it is nearer to the valence band. That means we can say that the distance of Fermi level from conduction band will be greater than 0.55 electron volt, but it is not equal to 1.1 electron volt. Okay. Now let's see another example. Two initially identical samples A and B of pure germanium. So we are having two identical samples, okay, A and B of a pure germanium, okay, and are doped with the donors to concentration of 1 into 10 raised to power 20 and 3 into 10 raised to power 20 respectively. This is the concentration given to us. These are the donor concentration, okay, in A and B respectively. If the whole concentration in A is 9 into 10 raised to power 12, then the whole concentration in B at same temperature will be. So we have to find the whole concentration in B. We are given the whole concentration in A, we are given a donor concentration, so that is equal to N is equal to ND, right? So and we are also given the donor concentration here in B also. So we also know the donor concentration of this. Okay, we have to find the whole concentration of in B. So we have already seen that according to the mass section law, N into P is always equal to Ni square. Now let's assume for first sample A. In sample A, the number of electron concentration will be equal to the donor concentration and is equal to 1 into 10 raised to power 20. Okay, and the whole concentration is given to us is equal to 9 into 10 raised to power 12. Okay, this is equal to Ni square. Also, if we see for the sample B, in that also the mass section law will be followed. Okay, and the electron concentration, or we can say the donor concentration, is given to us is equal to 3 into 10 raised to power 20, and we have to find the whole concentration, that is P, and it is equal to Ni square. Since we know that this Ni square will be equal to Ni square, so we can relate this to or compare this to equation. So we will get as 1 into 10 raised to power 20 into 9 into 10 raised to power 12 will be equal to 3 into 10 raised to power 20 into P. Okay, so from here if we see, this will be cancelled with this and 3 will be cancelled 3 times. So we will have the concentration of holes is equal to 3 into 10 raised to power 12. So we see the option A is satisfying our answer. And remember that the concentration is always has a unit of per meter cube. So this is basically a concentration per meter cube of an volume, we can say, right? So this is the answer for this question. Okay students, so in this part we have studied Fermi energy level and mass section law. In Fermi energy level we have seen that the level depends upon the types of semiconductor. If it is intrinsic or it is extrinsic. So depending upon this, the Fermi level changes. We have also seen mass action law. In this, we have seen that the product of concentration of electrons and holes is constant and is independent on the type of semiconductor. In the next part, we are going to study PN junction diode. So stay tuned with us.